Absolutely. But it was like very so I not explain that.
Okay, hi everyone. Hi, let's get started. Thank you. I forgot to write it, but the reminder is that the homework is due next Monday. And yeah, are there any issues so far? I know some folks have tried it and there have been some comments. Any problems? Okay, great, thank you. So if there's any problems, you can post on Ed discussion and yeah, there were some questions about like the size that I initially put of 1K by 1K matrices to test the tiling may not have been big enough to see the performance effect. So I suggested bumping it up to like 4K or 5K on Ed discussion, I think. And it's okay if you've already like submitted it and done it. Like you don't, as long as you implement the tiling, that's all I asked for. But just it was a little sad to see like negative performance effect on small matrices. So you might just try making it a little bit bigger. And it will take like a few minutes to complete at that size. So just be patient and wait a little bit. Yeah, thank you. And everybody should have turned in the pre-proposal today. So thank you. Yes.
So in the slide, of that planning chapter, the sequence of the loop is also IJK. Does that incur cache miss even if it's tile?
On the outer one or the inner one? The outer or the inner one? Should be IKJ, I think.
Yes.
Both should be IKJ. Yeah. Thank you. Cool. All right. So I have like a main lecture for today, but I just want to finish up what we talked about last time first. So there was a question about hyperthreading both on the chat and in person last time. So I just wanted to clarify a little bit. So hyperthreading is like an Intel specific version of something called simultaneous multi-threading or SMT. And hyperthreading is just like the Intel marketing name for it, which is when you have two logical cores for every physical core. So this is like a picture. It's small, but they're out of space. But the way it works normally when you have two cores, you have like two separate cores and they're connected by a memory bus. And each one of them has like state and they have stuff here, which is like ALUs. And when you have hyperthreading, there's only one set of ALUs, like that's not duplicated, but stuff like registers is. So you can do, the OS can do like co-scheduling of threads on this one physical core, but it has two sets of registers. So you can double the, like, if you're able to schedule it and if you have enough compute to saturate these two logical cores, then you can increase your throughput. Intel reported their first implementation, which was over 10 years ago, that had about 5% more area, but 15 to 30% better performance. Recently, I think it's more of a wash whether this actually helps you. And especially it really depends on whether your application is compute bound or memory bound, because this will not really help you if your application is memory bound, because it doesn't increase your like memory bandwidth or it doesn't improve your latency. It just gives you more like cycles to do mathematical operations. So yeah, and I think recently there was even some issue. I was reading this earlier today about like due to some security issue that I didn't fully understand, they suggest that you turn off hyperthreading in some cases because it may mitigate the issue. So yeah, so all this to say that some studies show that for applications that it doesn't find much benefit. So last class I was saying like you can multiply by 2 to get double the throughput or double the clock speed if you have hyperthreading. That's like a super optimistic thing that I was doing, but that was already like a back of the envelope thing. So yes.
I'm confused why it would not help if you were like, if like the application was compute bound. I don't see how it would help if you're not like increasing the actual like arithmetic you can do, because you still have the same amount of like ALUs. So how would it help?
You still have the same amount of ALUs, but you have more registers.
Sure.
So like if you were full up on registers with one set of,
but that wouldn't
unlike one
affect
core.
the amount of flops, like floating point operations you can do, right? For the same amount of ALUs.
If you were able to saturate all the ALUs already with one set of registers, then it wouldn't help you.
Okay. So that would be a memory bound thing, and then it wouldn't help. Is that what the thing is?
That would be a memory.
Or I'm a bit confused on, or like how, if it was compute bound, this would be effective, or if the application was. compute bound, yeah.
Maybe like if your application is super simple, like if you're just doing like multiplies and adds or something like that, like just one at a time on every thread, that might not help you that much because it's not really overflowing the registers. But if it's more complicated than that, it might help you to have slightly more architectural state. Because then it would be like if you just have multiplies and adds, it's easy to fill up your ALUs. But if it's slightly more complicated and you need a little more scratch space, then maybe that's the case that might help you. Yep, thank you. Cool. So that is hyperthreading. Hopefully that cleared up some stuff. And I just want to finish up what we were talking about last time, which is about the roofline. So if you remember this plot from last time, we have the roofline, which is like, it has two main parts. One is this slope, which is your memory bandwidth, and one is the peak, which is your flops. And applications are either on the left side or the right side, and the right side means that you're compute bound, and the left side means that you're memory bound. And before your optimization, your performance is limited because your effective peak in both bandwidth and clock speed is lower if you don't have stuff like SIMD in terms of clock speed, or if you don't have prefetching in terms of bandwidth, but you can increase your effective peak in both by doing optimizations. Yeah, so just a couple of small examples. So let's say you have this simple parallel for loop. You have n iterations, and you have a bunch of arrays, you have X, Y, and Z, and for every iteration of your parallel for, you're basically adding the elements of X and Y together. You're maybe like multiplying by a constant, but that's just, alpha is just a constant, and you're basically doing like element-wise addition into Z. And so the way that you calculate your intensity is that you have two flops per operation, like addition and multiplication, and there's 3 memory references to X, Y, and Z, 2 reads and 1 write. And if they're 8-byte elements, 3 elements at 8 bytes each is 24 bytes. And you have 2 flops, and you have 24 bytes. So intensity is flops over bytes, and that's about this 0.08. So the intensity is very low for this very simple element-wise addition. And it would probably be low on the memory bound side of the roofline. Okay, so let's say that we had a slightly more complicated computation that we wanted to do. This is heat stencil. So stencil computations are a common thing in scientific computing. Basically, the way they work is that you have an array and you compute some point in your destination array based on some aggregation of points around you in your source array. So this is like the pseudocode. You have some array next, and you have 3 dimensions, X, Y, and Z. And the way you compute next is through 7 points. Like this is your current point, X, Y, and Z, and there are 6 other ones like -1, +1 in each dimension. So that's how you get 6 other things. And current is like your starting array, and C0, C1 are just constants. So this is a 7-point stencil. And in your 7-point stencil, for every iteration, you are doing 8 flops. So 1, 2, 3, 4, 5, 6, 7, 8. And there are 8 memory references. So this is 7 elements that go into your input and 1 for your output. So that's 8. And the way you do the intensity again is 8 divided by 64 if you have 8-byte elements. So that's 0.125. And it turns out that you can do cache blocking, which is basically like, rather than doing, like you would imagine the most easy way to do this is with 3 loops, but you could do a similar tiling scheme for stencil computations to get better locality in cache accesses. And if you do something like tiling, then you can filter your accesses in the cache, and you can increase your intensity close to 0.5.
The intensity is based on, I was under the impression that it was not like based on memory necessarily, but like just accesses. So like a greater cache hits could increase the intensity.
Greater cache hits could increase the intensity because yeah, the bottom thing is bytes accessed from DRAM.
Oh.
Thank you.
Can you post this?
Oh, yeah, sorry. This thing? Yep. Great. Okay. Yeah, so using something similar to tiling, you can increase the intensity by decreasing the access to DRAM. Oops. Okay, and yeah, so this is just like an example of where your stencil would fall on this roofline example. So it's further right than the original loop, and it's still pretty low. This is still less than 1 flops per byte, but the constants matter, so you're further up on the roofline, so you can get more access to your gigaflops. This is just an experimental example. So they ran the empirical roofline on a bunch of architectures. So they ran this on with Xeon and NVIDIA. And this is the 7-point stencil here. And you can get even more complicated. This is 27-point stencil. Sparse matrix vector multiplication is all the way down here. So the intensity is super low. And DGEM, which is dense matrix multiply that we were talking about for a while, is all the way up here and here also. So that's kind of what intensity looks like. Okay, so to wrap up the part about the roofline tells you the upper bound on performance as the min of two upper bounds of the machine, which is flops and peak memory bandwidth, and arithmetic intensity, which is flops over the number of bytes that you have to move from DRAM, is a key part of the model and usually defined as this best case scenario for your application. And originally the roofline is for single processors and shared memory. And there's a really interesting question on the discussion board, which is, can you do it for distributed systems where you have to also care about communication? And the answer is yes. Some people have written papers about it. I haven't read them in depth, so actually I don't quite know what they say, but that is a natural and interesting extension of the model. And the roofline is widely used in practice and can be adapted to anything when you have bandwidth and compute limited situations. Cool. Does that make sense? Okay, so we are done with roofline for today. This is exciting. So today, the main topic that I want to talk about is IO efficient data structures. And this is exciting for me because this is like one of my favorite topics. So yeah, because I work on data structures a lot. So we can remember this ideal cache model that we were talking a lot in the context of matrix multiplication. We have this two-level hierarchy. The memory is of size m bytes. Sorry, this one is of size m bytes. You have b size cache lines. So you have m over b cache lines. And you measure performance in terms of memory movement between flow memory and cache. And you can move data in blocks of size b at a time. And it costs you, moving one is like unit cost in this model. And so you have two performance measures. You have work, which is what you would do in the RAM model. And then we have cache misses Q, which is the number of cache lines that we have to transfer. So that's what we were doing the analysis of tiling and divide and conquer for matrix multiplication. Okay. So dictionary data structures are this classical API for data structures that we all learned in our introductory algorithms class. This general purpose data structure for storing a group of objects. Dictionaries usually support these following basic operations. You have search, which is like find whether the element is there or not, insert an element, remove an element. And there's like a couple of variants of this, but so you can have keys and values where keys map into some value, like in this example, it's a string. If you just have keys without values, it's called a key store. If you have both, it's called a key value stores. Yeah. Okay, so this is just a recap. I think everybody here has probably done algorithms, but self-balancing binary trees are this classical paradigm in data structures. They support all the basic operations like search, insert, delete in log n time. They're self-balancing, for example, like red-black trees or AVL trees, stuff like that. And I'm not going to explain how they work. You can read CLRS to have an in-depth understanding of how they work. But basically, they all rely on this algorithm. Like they don't let the depth get too large. And so usually you have to do some kind of rotation to maintain the depth. Okay, so how many cache misses does it take to search, insert, and delete in one of these?
Okay.
Yes, good. Yeah, so in a balanced binary tree, there's one pointer per level, and therefore you have one cache miss per level. So you have to do an indirection, and the height of the tree is log n. So every operation takes log n cache misses. Yeah, I want to talk about skip list for a little bit. I'm not sure if everybody knows about these already, but I want to talk about them anyway. Okay, so a skip list is it's again in the RAM model. It's like a RAM optimal data structure. It stores a set S of elements in a series of lists. And every one of these lists has endpoints, which is positive infinity and negative infinity. And the bottom level holds all the elements in a sorted linked list. And every subsequent level holds some subset of the lower level, like the elements one level down. So the way that I learned about this is kind of like a subway. So like the bottom level is like the local stops and the higher levels are like express stops. So only, all the elements are in this one and fewer elements are in the higher levels. And this is one way that you can implement dictionary data structures. And the way that you would implement these in code is with quad nodes, which means that you have 4 pointers, 3 pointers, I guess. You store the actual thing. I guess if it's doubly linked, then you have 4 pointers, you have before and after, you have up and down. You could also just have down and right. But then you wouldn't be able to go backwards for like predecessor. And yeah, and then there's also like the endpoints, infinity and minus infinity. So those are special endpoints that tell you when you're done with the list. So the way that you search in the skip list goes like this. You start from the top level, you start from negative infinity. And if the thing on your right is less than the key that you're searching for, you step right, otherwise you step down. So at the top level, positive infinity is bigger than the thing. Oh, we're looking for 78. So positive infinity is bigger than the thing that we're looking for. And so we go 1 level down and we see that 31 is less than 78. So we go to 31, but positive infinity is still bigger than that. So we drop down again and we do a similar procedure at every level until we find 78 in the bottommost level. And if we get all the way down to the bottom and we don't find the element, then we just return no. Otherwise, we find it and we return yes. To insert the item in the skip, insert any item in the skip list, we use some randomized algorithm. So when an element comes, we toss a coin until we see tails, and then the number of times we saw heads is some variable I, and that's going to tell us how high we promote the element. So that tells us how many levels the element will appear in. And that's like a randomized thing, you just flip coins. So you don't have to do any balancing for that. And yeah, so basically the way it works is like you do a similar procedure as search, but as you go down, you insert it at all the levels that you flip the coin onto. So in this example, we insert 15 and I equals 2. So 15 goes into level 0, 1, and 2. Okay, so like I said, randomized algorithms control the algorithm through, oh, I'm sorry.
So like here, would you like, so you start at S3 and it's not, well, I guess you don't have to start at S3, but like you go to S2 and then you see you just insert it there and then you see there's no like element beyond, until like plus infinity, so you can put it there and you can connect it there. But then, and then you, from 15, like how would you find the pointer to like 23? Or I guess you wouldn't need to find the pointer to 23 necessarily, but.
Oh, so you would stay like in the code, you would be at negative infinity and you would hold on to next. Next would be positive infinity for now, and you'd save next. And then you'd set next to 15, and then you set this next to here.
Yeah.
And then you drop down this way.
And you drop, okay, so
You
you
drop
do
down
that
at
for each
negative.
level.
Yeah,
Fine.
you drop down one before, because yeah, you're right. Like if you lose that, then unless you have a back pointer, then you don't know where to put it in the lower level.
Okay, but then insertion, like, would you, for like S0, would you have to like go through the whole list, or how are you finding
I
it?
think lead code has a skip list problem. If you I don't, yeah, because I remember implementing it on lead code. It's actually, I think I did the 3 pointers. I think the up one you actually don't need. But yeah,
So you don't have to search from negative infinity at S0. You keep dropping down similar to the way that you did in the search. And then you ideally like get closer.
The next one, so yeah.
it's definitely possible. Maybe more than that.
No, it's a good question though. Like, unless you think about it, if this is like your first time and you don't think about it that hard, then it's a little complicated. So,
My friends online are asking if you could slow down.
oh, of course, yes. Do you want me to go back to any of the slides? Okay, sure. Yeah, so skip lists are randomized data structures, and randomized data structures depend on randomized algorithms, which control execution through random selection, like coin tosses or die rolls. And this is like the high level way that they work. You generate some random bit, and if the bit is, you do something different based on if your bit is 0 or 1. And in that case, the skip list height depended on your sequence of bits. The runtime of your randomized algorithm depends only on the outcomes of your coin tosses and dice rolls. And the way that you prove things about randomized data structures is through probability. And you prove things like an expectation or with high probability. And usually in the analysis, you make assumptions like the coins are unbiased, which means that they have an equal chance of being heads or tails. And they're independent, which means that coin tosses don't affect each other's outcome. And usually you make claims about expected running time, which means that in most cases or in the average case, in some sense, that's the running time you're going to get, which is not the worst case running time. Because in the worst case, like a skip list, everything could be at every level if you just always tossed heads. And that would be really bad because you wouldn't get better in your insert, but it has very low probability in that case. When you have randomization in data structures, they're referred to as probabilistic data structures. And I'm not going to prove this now. I have some slides at the end to prove this if we have more time, or you can read them on your own time. But we use this randomized algorithm to insert and delete into a skip list an expected log n time. And the high level argument is that like you have log n levels, and at each level you don't need to go that far. So the expected time is log n. The height of the skip list is log n with high probability, which is a stronger claim than with expectation. So expectation is like an average claim, average case type of claim, and high probability means that the probability depends on n and goes to 1 as n goes to infinity. So like as your data structure gets larger, high probability means like this is a almost certain event. And the expected space usage, again, which is an average case thing, is order n, and the high level way of how that works is that like the bottom level is clearly n because it stores everything, but as you go higher and higher, they get smaller and smaller, and they're asymptotically decreasing in expectation as you go up. Okay, so are binary trees and skip lists optimal in the ADL cache model?
I would guess, I guess no, because I feel like there's a lot of like fragmenting, that would not be, good in like the cache cell.
Yeah, yes.
Yeah, I'm assuming like for an array, everything's like contiguous next to each other, but like for a binary tree or skip list, these pointers can be allocated in like other locations. So like when the cache puts stuff in the cache, it might not necessarily be the next element you're expecting.
I guess it depends on what you define as optimal, but like you mentioned, pointer chases are really bad. So I think it's possible to, because we've been not really talking about any of the memory layouts of these. So if you do some type of clever optimizations, like using some type of heap as like the underlying memory layout or something like, I can imagine that you could make the binary tree, you can make it work a little bit more like a heap, or make it work more, work better for a cache. If you know the cache is there, you can make it work a little bit better. But just by default, I think they're not optimal. But we also have to find what optimal means.
Good point. So I will talk about what optimal means. Yes, exactly. So as you say, they are not optimal in the external memory model because you have to do pointer tracing. So at a high level, like if you remember in the ideal cache model, you have these cache lines. And in a perfect world, you would get like B elements per cache line. But with pointer tracing, you get 1 element per cache line, which is the reason that they are not exactly optimal. So B trees and B plus trees are this classical cache-friendly data structure. And B trees are a self-balancing tree data structure that kind of like, sort of like weight balance trees, like AVL trees. They keep data sorted, just like regular balanced binary trees, and they allow you to search, do access, insert, and delete in log base B of n. So previously we had log n for balanced binary trees and skip lists. There's now a base B in the log. And basically the way they work is they're like B trees, but instead of 2-way fan out, they have B-way fan out, where B is your cache line size. And they're optimized for systems that read and write large blocks of data, which is all of them nowadays. At least you have cache lines, and on disk, the blocks are even bigger. So the fan out depends on which setting you're in. Yes.
So like we're still pointer chasing, but instead like we're getting B elements per.
Yes, exactly. I'll show diagrams in 1 second. Yeah. So as you said, like they're still based on pointers, but now instead of previously with binary trees, like you had 2 children per node, now you have B children per node. And so this is one contiguous block. But now each one of the elements in here has a child, and it points to another one of these blocks with the children in it. And so on and so on. And the bottom level, just as in regular trees, is called leaf nodes, and everything above the leaf nodes is called internal nodes. And every node has B-way fan out. So the height of the tree is log base B of n. So like remember with binary trees, the height is log base 2 of n because you branch out 2 every time, but now this is log base B of n. So that's why you get that height. And there are n over b leaves because there are n elements and each block holds about b elements. So there's theta n over b leaves. Oh, and the elements inside the internal nodes are called pivots because they tell you which direction to go when you search down the tree.
Which will be, are we assuming that, the only, nodes that will have fewer than B children are the ones that hold leaf nodes, or, like, are we assuming that it'll fill up like a heap, like, or? That was some, or are these still true even if some of the internal nodes don't have B children?
The invariant, the way that B trees grow, as long as the total tree has more than like B over 2 elements, every node.
Like, when it has.
In the steady state, every node has theta B elements.
Yeah, like, as it grows and self-balances, it makes sure that everything internally has B, and then only things that don't have B are like a 1 or 2.
Yeah, like only the root can have less than B.
Okay.
Yeah, I'll talk about that when I talk about like how you insert into a B tree. And hopefully that clears it up, but then we can revisit it if not. Yeah, so that is B tree. In practice, we often use something called the B plus tree, which is just a variant of a B tree. And the only difference between B plus tree and B tree is that in the B plus version, all of the elements appear in the leaves, like sort of like in a skip list, everything was in the bottom, as opposed to like a binary tree, not everything is in the bottom, like stuff is also inside. But in a B plus tree, stuff is repeated up above also. So everything appears in the leaves, and sometimes when the leaves get too full, an element gets copied into one of the higher levels, and that's how you get the pivots. Yeah, and in a B plus tree, the leaves are also connected with pointers just horizontally from left to right, so you can easily traverse all of them in order. So just like in a binary tree, or any data structure really, searches begin at the root, and you do comparisons to direct it into a leaf. But in a binary tree, you only have left or right. But in a B tree, you have many pivots. So like in this example, you have 14, 19, and 24. And like you have left, which is everything less than 14. You have here, which is between 14 and 19. You have here, which is 24, and there's nothing after it. So this is like 24 to infinity in this example. And this is the root, this is the highermost level. And in this example, if you're looking for 15, you would first go to your root, you would see that 15 is between 14 and 19, and you would drop down here and search in this leaf. And again, the nodes are size B. Every node is of size B, so there's more than 2 elements in each one. And based on the search, we can find that 15 is not in the tree based on how we follow the pivots.
And it looks like skip list.
Kind of a skip list. In that we copied the front of everything. Yeah, so this is a B plus tree because like stuff is repeated up above, and also there's pointers left and right. Yeah, it is like a skip list, but there's no coin toss.
So in this example, would there be like 2 cache misses then, since we're like loading the root and then
Yeah, so assuming like if your cache line was size 4 elements, then you would first load the root, which is 1 cache line this. You would have to load this, which is another one, exactly.
So, I mean, does that mean then like when you're designing a B plus tree, like you have, it has to be specific to your hardware?
You have to, for asymptotic benefit, you have to set the node size to be theta B, where B is like a cache line size or your disk block size or whatever level of cache you're at. Yeah. Doesn't have to be exactly 64 bytes, but it has to be around 64 bytes. So we're gonna do an example of how you would insert elements into this B plus tree. So let's say that we want to insert 8. And so, okay, so we find that 8 is less than 14. So we're going to follow this pointer down. And unfortunately, now this leaf is full, so we can't put eight, like, if there were space, we would just put it at the end, but it's full, so now we need to split this node. And so we split this page, we split this leaf, and we put half of it on the left side, so that's 2 and 3. We put the other half of it in the right side, which is 5, 7, and 8. And now we have two things here at the leaf level, that 14 down here, or sorry, that this left pivot is pointing to at 14. But now we need to promote something one level up, because this 14, like, you need one pivot per node. So we're gonna have to move something up. And yeah, so like I said, we need to fix up the pivots. And because 5 is the front of this leaf, this new leaf that got created, we're gonna move 5 up here and shift the pivots around. And so now, with these elements here, like this pointer now, this pointer was originally the one left of 14, but now is the one left of 5. And the one to the right of 5 is something new. So this is pointing to the new node that we made. Does that make sense? So what if we wanted to insert this element 21 into this B plus tree? So we're gonna go follow this pivot because 21 is between 19 and 24. And we go here, and again, we have the same situation. This leaf node is full, so we're gonna have to split it. So we do the same thing that we did before. We split the left half and the right half, and 21 happened to go on the right side, so we put 21 in the front because this maintains the order. And now that 21 is in the front, we're gonna promote it again. And we're gonna promote 21, but this thing also is full now. So we're gonna kind of recursively go up the tree using the same procedure that we were doing for the leaves. So we, again, like we split this thing in half, and yeah, so this 19, am I already out of time? So this 19, so I guess one subtle thing is like this pointer was 19, or this pivot was 19 before, but now 19 gets moved up one level because you need to promote something else into the new root. And now that we split this thing into halves and promoted 21, 19 was the front of the rightmost thing. So 19 gets promoted into the root and we recursively go up. Yes.
So the fan out is 5 for this B tree, but I thought we said B was 4, or is it?
B is 4, but
It's
it's like
5.
+1 because there's like a min or a max depending on how you look at it.
Well, like on the previous slide when it showed 5, or
Sorry.
like here, this node is 5 children. Or, no, like for the top, at least the top, right?
Yeah.
It has 5 children.
Every internal node has B pivots and B+1 children
Oh, okay.
because you need to go either min or max. But every leaf only has B elements because there's no pivots needed. Yep. And so, yeah, so we cursively do the same thing again, and now we get a new root because we had to promote 19. And that's how you get new levels in the tree. Did that answer your question?
So the fan out is actually up to B+1.
Mhm.
Okay.
Yes.
But the elements are is B elements, which are either pivots, or they're either pivots or the actual data members.
Can you say it again?
Wait, if the fan out is B+1, why did we do all the calculations based on fan out being B, and then B plus trees, the fan out is B+1?
For both B and B plus trees, the fan out, the number of children is B+1, but the number of pivots is B. Because
Does
like,
fan out mean number of children? Or no? I thought, I'm used to fan out meaning number of children.
yeah, fan out is number of children.
Mhm.
I guess like in terms of asymptotics, as long as the fan out is theta B, you're good.
Okay.
Because like the height is log base, it's like theta log base B. So B+1 is theta B.
Mhm. Oh, like theta B just means B+1?
Theta B means like a within a constant
Okay,
factor of B. Yeah,
Yeah, I guess.
yeah, but B+1, it happens to be theta B. Yeah. So, yes.
It's B+1 pointer, one present, one cache line.
No, so you would need to read another cache line. Well, you would already need to read 2 cache lines because one is the pivots and one is the pointers. Make sense? Like pointers are not 0 bytes, pointers are like 64 bytes or whatever. And so like, this is like in some sense, it's like a practical thing, but in the asymptotics, you just count it as like order B, because like you think of it as a constant factor more than the number of elements that you have. But yes, so it is technically more than exactly one cache line, but it is actually okay because prefetchers are surprisingly aggressive. So it turns out that if you prefetch one cache line, it will just like prefetch the next cache line for you pretty much always. So if it's like 2 or even 3, it turns out that it's actually totally fine. Yeah, good question. Okay. And yeah, so B trees are this cache-friendly data structure. They support searches and inserts and log-base B of n cache line transfers. And most updates only write to the leaves because most of the time you don't have to propagate something up. You only have to propagate something up every B insertions. But in the worst case, you have to propagate all the way up. So you may have to write log-base B of n levels in the very worst case, but that only happens like once every n insertions. Okay, and notice that this log-base B of n is little o of log n, which is what we got with binary trees. Okay, so this is your question, which is, are these optimal in the ideal cache model? Yeah, so there's a bunch of ways that you can think about organizing your data. This is a cartoon, but like, so you can imagine like this thing is, you can just like, you store your data and you can easily add to it, but you get really fast like insertions in some sense, but you can't find stuff. And then this again is like on the other end, you organize stuff, so you can find stuff fast, but you have to be careful when you add stuff. And so these are like two paradigms in data structure design. The left one is called logging, which is like if you just imagine that you had an array and you added stuff to the end of it every time you got something new, that would be like order 1 insert, right? Because like you just add to the end, but if you wanted to search something, then you would have to do order n because you have to look through the whole thing. And on the other side, like this is B trees. So B trees are like organized and they're worse in insert, but better in search compared to logging. B trees are called indexing. Or I guess like indexing is the higher level paradigm for B trees. Okay, so like I said, you have insertion and search, which are two operations that dictionaries can do. And for logging, your insert is 1 over B because you're just appending to the end, which is great. But unfortunately, that is worse than searching it, or that is better than inserting in a B tree, which is log-base B of n. But on the other hand, your search needs to go through the whole log, so that's n over B, which is worse, or like it's better to search in a B tree, so that's log-base B of n. So like in some sense, like optimal is like there's no optimal for one single operation, because like you can always do better if you pay in the other one. And it turns out that there is like this trade-off between insertion and search in the ideal cache model. And there's this paper from 2003 that proves this trade-off curve. So on one end is the B tree, which has fast queries, but slow insertions. And on the other end is logging, which has very fast insertion, but the queries are really slow. So yeah, and this is like a cartoon to illustrate it, but this is actually like a mathematical thing. And they show that you can write this trade-off as a function of epsilon, where you can, this is the lower bound on how well you can do in both insert and point query, and it's a function of epsilon. So a B tree is the case when you set epsilon equal to 1. So that is log-base B of n in both cases. And if you set epsilon equal, but you can set epsilon equal to other things, and that gives you different data structures. So if you set epsilon equal to 1/2, for example, you would get log-base B of n divided by root B for your insert, but this would still be order log-base B of n for your point query. This would be like a constant factor bigger, but still in the asymptotics, that constant factor goes away. And similarly, you can set epsilon to 0 and you would get some other bounds. That would be log n over B for epsilon equals 0. Does that answer your question about optimality?
Somewhat.
Could you say your question
So
again?
I'm just thinking about epsilon.
Oh.
So, no.
Epsilon is like, it's just like I'll explain more about epsilon, but epsilon is like a parameter that we can use later to design other data structures. Because like, in some sense, epsilon is like how full is your node.
Mm.
And 1 means your B tree is totally full at every node.
Like, what is hash maps? Like, for instance?
wouldn't hash maps break this? This is, good point. This is in the comparison model. So like if you have to store a sorted list, then you have these lower bounds, but a hash map, indeed, if you don't have to store them sorted, you can do like order one insert with probability guarantees, whatever. And you can do, of course, the same point queries in a hash map. Exactly. Good question. Yeah. So if, yeah, these are like sorting lower bounds in the ideal cache model, just like we have like n log n sorting lower bounds in the REM model. But hash maps also break those. Mhm. Yeah, good question. Okay, so like I was saying, you can vary this parameter epsilon, and the thing to note is that here, for the epsilon equals 1/2, you get asymptotically the same point queries, but you get asymptotically faster insertions. So we're going to use that for to make fancier data structures. Here, setting different epsilon, you can improve your insertions with almost no loss in point query performance. And I'm going to talk about how to do that next. Okay, are we all good on B trees? Because you need to understand B trees to understand this next part. Yes.
Why do we need the pointers in all of the leaf nodes to other leaf nodes?
They're not necessary, but they are, if you want to do like a large range query across leaf nodes, like if you want all elements between like 1 and 100, for example, it is faster if you have those leaf level pointers.
I mean, can't we just do like
You can go like
order
up and down. You can do
traversal?
like in order traversal, it's true. But then you have to do more indirections to do your in order traversal.
Oh, I see. Yeah, that's what.
And maybe asymptotically it's fine. It might like get washed away. It might get washed away in the asymptotics, but in a practical sense, it's better to just not have to
Yeah, I
traverse
mean,
extra
theoretically
nodes.
it's the same, but practically probably is
Yeah,
like-
you might have to read like a constant factor of extra nodes or something.
Yeah, but the thing is that if you got too few elements in a leaf node and then you got a rebalance, so you probably want to just directly know where you want to put the element to like register or like.
Yeah,
Yeah,
exactly.
that's why you just go directly there instead
Yeah.
of traversing.
Yeah, and it makes your split easier. Because otherwise you have to like find next and stuff.
Where do probabilistic data structures fit in like Bloom filters?
Where do Bloom filters fit in? Bloom filters are not dictionaries. So dictionaries are like a loss-free, I guess lost list dictionaries allow you to just like query for key and value upfront, but Bloom filters just tell you about existence.
But you can still have like the value as a second map to the first stage.
Yeah, you can have like invertible Bloom, like lookup tables, but I mean,
Like, well, I guess with Bloom filters, there's some error. Like you might have false positives in the Bloom filter. So, yeah, but there is some work on, like you said, like invertible Bloom, where you can attach some lookup table. But I'm not totally sure about how that works in the presence of error. Maybe there's also some error in the value lookup,
yeah,
probably.
alright, there's not error, there's like. The value might not exist, you might not be able to get it.
Yeah, but Bloom filters are also, I guess for the people who, Bloom filters are this data structure where for every element you store a couple of bits in some array. And so then like you store these bits, but you don't store the actual element. So if you want to query for existence, you just check the bits based on some hash function. And, but the problem is that you might get false positives because if other elements also happen to hash to the same bits, then you might check that it's yes, even though the thing is not actually there. And so if you see yes, then you still have to check the data structure, but if you see no, then you know it's not there. So it's like one-sided error. Does that make sense? Cool. Yeah, so next I wanted to talk about B epsilon trees, which are a variant of B trees that allow us to achieve the asymptotic benefit that I showed with a different setting of epsilon in the trade-off curve. And B epsilon trees are one type of data structure under a larger class of data structure called right optimized data structure. Okay, so B epsilon trees are search trees, much like B trees. And again, they have pivots like B trees do. And they have internal nodes and leaf nodes, and this happens to be like a key value store. So these are the keys and these are the values, and these are the leaves in the B epsilon tree. And not unfortunately, but like different from B trees, like in B trees, you fill the entire thing up to B. But in B epsilon trees, you allow only B epsilon number of pivots, where epsilon is subsetting. You can think of it like a half. So for simplicity, like you have only root B pivots, and the rest of it is buffer space. And yeah, so the height of the tree is still, the height of the tree is log base B epsilon of n. But if epsilon is a half, that's still order log base B of n. So you have these pivots in the internal nodes, and you have some empty space in the internal nodes. And the leaf nodes you can fill up to B.
So the branching factor, would that also be B epsilon or would
Yes.
it be epsilon?
Yeah, it would be like B epsilon plus 1, I guess.
Yeah.
Exactly, yeah.
We just graph B equals to 8, and B epsilon should be 0.5.
I guess here, B, if epsilon is half, B epsilon is 2. And then,
Epsilon's one third. The third root of A is 2.
yeah, I guess so, yes.
But the branch, yeah, branch says
But one
two
of the
plus
leaves says an element, isn't?
one.
No, this is, each of these is one element. Like the top and the bottom is one thing. This is the key and value. Yeah.
So and how exactly do we utilize this rest buffer that we have in internal nodes?
I will tell you in 1 minute. Yes.
Yeah.
That's it. Okay, yes. Okay, so yeah, is everybody good with this high level idea? Just like we keep some empty space inside the internal nodes, and we're gonna use this buffer in the insertions. So, okay, so when insertions first come, they get put into this root buffer. So suppose we got this element, the key is 94 and the value is 4. So this thing comes here, and normally in a B tree, we would have to go all the way down and find the leaf where it goes and put it there and maybe do some promotion. But for now, in this B epsilon tree, we're just gonna put it here. Okay, so it goes there, and we get some more stuff, and you put it all in the root buffer. So I guess in this case, B is 6. Yeah, B is 6
Yeah,
in
I
this
think it's
case.
just like in the.
Yeah, B is 6, and then the number of pivots is 2. Yeah, so maybe it's not exactly like a exact power in this case, but I think it works, like the proofs work for any constant power or constant epsilon. Maybe this is just for ease of illustration. Okay, so now our root node became full. And when the buffer becomes full, what we're going to do is we're going to choose the child that receives the most messages, and we're going to flush those into the child buffer, the target child buffer. So here, 39 and 64 are these two keys, and they're going to go into this child. And that is the child that is going to get the most messages because 94 goes here and 13 goes there, but each of those is just going to get 1. So we are just going to take these and move them 1 level down. And so like, we're not going to flush everything here. We're just going to flush the target child with the most messages, but we're guaranteed that by like pigeonhole, this is going to be at least root B. Okay. So we took those and we moved them into the target child buffer. And now we get some more stuff. This is 66. This is 65. Okay, so now the root is full again, and we're going to flush those into the child, which is happens to be the same thing, this one.
I don't understand why 94 isn't done.
94 doesn't move down because the procedure is just to pick the child that gets the most messages. Because otherwise you're going to have to read all of the children. And to prove our asymptotic balance, we only want to read 1 child per flush.
Do we do the flush when, on the insertion that inserts it, or on the next insertion, does that matter? Whether it's like once we make it full, or when we actually need to use it?
You can do it either way. From an asymptotic point of view, for now, it doesn't matter.
I don't fully understand why the middle buffer is the one that receives the messages as opposed to the left buffer, if that makes sense.
Because that's
middle
where those
buffer.
would go. like,
Because the
39
pivot,
keys.
You
Yeah.
know, like everything that's less than 37 goes into the left child, everything that's between 37 and 86 goes to the middle child, everything that's larger than 86 goes to the right child.
Oh, I
So-
see. Okay.
The value on the bottom. doesn't matter.
Yeah. That
Yeah.
makes sense.
yeah, exactly. Thank you. So yeah, you determine like in some sense the range based on these pivots, like there are 3 children here and these elements that were here happen to fall into this range of like between 37 and 90. 86, I guess. 86. Yep. Thank you. Okay, so we got some more stuff and that got flushed down and now this is full. So in this case, we're gonna do the scheme that when it becomes full, we're gonna flush, but you could also wait and then flush on the next time when you flush stuff into it. Yeah, so now we're gonna do the same procedure again, just 1 level down. We're gonna pick the thing that gets the most messages, and that's gonna happen to be this one, based on just like the same way that we determine the ranges 1 level up, and you're gonna flush these elements here. Okay. Yep.
So do we flush certain number of elements or all elements that come into the certain range that's specified?
You're gonna flush all elements that fall into the max. You're gonna flush all elements that will go into the child that receives the most messages out of all the children. So like, let me go back. So like here, every one of these elements falls into some range based on the
Yeah,
pivots.
that's
Yeah,
fine. So it's like it's not the constant number of elements that you're gonna flush, it's always.
it's always variable and you have to figure out how many it is. But you can like, with 1 pass, you can count like how many are going to each child. And you just pick the one that's the highest. Okay, so again, we're gonna flush 1 level down, just like we did before. And that is going down. Okay, so that's how insertion works. And then you just keep repeating this procedure and you flush all the way down to the leaves.
So, and how often and how exactly do we check the frequency of successes of elements? Because like to flush, we would need to check every internal node to see whether like inside this internal node, this and this elements got more excesses than the certain threshold, so that we flush it, right? So like in every iteration, we'll need to check every node. What probably doesn't happen because
You only need to check your own node because you have the pivots. The pivots tell you which range that you'll go to.
I think the number of accesses matters.
What do you mean?
You mentioned the number of accesses.
Yeah, can you quickly go back to the previous slide? I mean the most messages, but I mean.
I think they're calling like elements messages.
Yeah, so element, yeah, I'm here, messages means like number of key value pairs.
Okay, I got it.
Thank you.
Okay, because I was thinking about the acceptance.
So how frequently do the pivot ranges change? So like after you flush, do you change the ranges so that like, for example, does the right of the topmost node, does that pivot like have to do with 94? Or like you have to wait until you get off 13?
You have,
So for example, right now, 86, like all numbers greater than 86 go to the rightmost node.
Mhm.
So after you flush those elements, you do all numbers greater than 94 now go to the rightmost node. You add more elements to the tree.
so if you got more stuff here, and it happened that this was the thing that you're flushing into, all elements greater than 86 would go here.
So it's still 86. It doesn't change based off.
No, not unless so the promotion scheme works the same as in B-trees. We do the same thing, like if the leaf gets full, then you have to promote 1 level up, and that's how you determine the pivots in the internal nodes. So the pivots might change if you get a lot of stuff in the leaves, and then you have to push stuff up. Does that answer your question? Thank you.
Just to confirm, like all of these pivots came from some leaf node that like had leaf node.
Exactly. Modulo, like in the very beginning in the startup, like there's only 1 node,
Yeah.
like that's the root and the leaf and everything.
They have values as well, it's just not illustrated.
Yeah. Yes, it's not illustrated, but here, this is not a B+ tree, so they also have values. You could implement this either in a B+ way or in a B tree way, but this happens to be in a B tree way.
Then like in each node, you just put them wherever, like is there any benefit of like keeping it sorted?
Like in the buffer, you
Yeah.
mean? You could, in this illustration, they're not sorted. You don't have to keep them sorted. I guess one benefit would be if you're searching, then it's easier to search in a sorted list. But the trade-off is like then you have to maintain the sorted list in the buffer. So I think from an asymptotic point of view, since each node is theta b, it doesn't matter in asymptotic sense, but from an implementation point of view, like if you were implementing, then you would have to consider that trade-off.
Are the pivots on the key or the keypad?
In a B tree, the pivots have to be key value pairs because not everything is in the leaves. This is a B tree because like not every, like here, for example, like 75 is a pivot, but 75 is not in the leaf. So the 75, it's not pictured, but it also has a value attached. Thank you. Cool. So that's how you do insertion. And it's basically like a B tree, but with buffers attached to each node. And the way you do lookups is similar also to B trees, but in addition to just checking the pivots like you did in a B tree, you also now have to check the buffer. So this is along with your question, like when you look in the buffer, if they're unsorted, you just have to check everything. If they're sorted, you can stop, but then you have to think about that when you do the insertions.
So this doesn't provide, I guess we didn't have discussed previously, but uniqueness is not something that is addressed by default.
Yeah, so exactly. So when you have an element, you might have repetitions higher up in the tree because like it might not have gotten flushed all the way down. But the way this works is that the newer things are higher up. So you can exit once you find it.
During this tree, have you not lost the advantage of sequential access if you're trying to access every single key?
Yeah, so if you want to access every single key, you have to do like an in order or pre-order or some kind of full tree traversal. But you have to do that also on a B tree, but not a B plus tree. So you could, I think even if you implemented this in a B plus way, you would still have to traverse the buffers. Yes, so that is one trade-off with this. Like if you are doing giant sequential range scans, this may be a bit challenging because you have to check the buffers.
Don't you have like the large root nodes are connected to the pointer?
So this level might be connected, but not everything may have made it down here. Yeah, it's a good question.
As a key value store, are you concerned with duplicate?
Sorry?
As a key value store, are you concerned with duplicate?
With duplicates? Yes, duplicates may appear in the buffer, like, for example, like if something is here, if we got, for example, 74, that would go in this buffer up here. If we search for 74, we would find it here first, but that would be okay because this came earlier, or later, sorry, later. More recent stuff is higher up in the tree because it hasn't gotten flushed down yet.
Yeah, no. You don't want duplicate in the for the same.
Well, they're saying that like you might allow duplicates to overwrite the
Yeah.
previous entry.
So like, yeah,
This
when
makes them
when duplicates like collide, you would overwrite the old element with the new element, but you may, so from a space usage point of view, there may be some issue, but you're guaranteed at most one duplicate per buffer, because like you can check for uniqueness within a buffer. And so like you would have one copy at most. In the very worst case, you would have one copy like all the way up the tree, but it's hopefully unlikely.
So we don't check if elements has already exited in the structure, we just directly insert it into the root file.
You can check the buffer for duplicates
Yeah.
with no extra asymptotic cost. But you cannot check lower down in the tree.
So doesn't this give like a LIFO behavior of like duplicate keys?
Could you say it again?
Doesn't it give like a last in first out behavior of duplicate keys? It's like if you add in duplicate key, like that's the one that you're serving until you delete it. Then you're gonna go down one row, find
Oh, that's a good
the
question.
second version of that duplicate key.
Yeah, delete. If you delete, we have to delete all duplicates. Because update works with insert and query, but delete,
Yeah.
your point is if you delete, it might only delete the most recent.
Yeah.
So the way
Maybe
that
you want that.
the way that deletes work,
That can be changed.
which I think maybe I have slides also, but the way that deletes work is that you put another message called the tombstone that tells you the element and deletion, and then you flush that all the way down. So you're guaranteed to get rid of everything.
When you push down a duplicate, you have to traverse the entire thing. So say if you were to push 79 third to fourth, you have to third get that thing. To take it 79 then. And then
Like,
okay.
you're saying if you push this down to here,
So we were
You would
17
check this
only
node,
be that buffer. So you only
17
touch that buffer.
yeah, 79 could only be here,
Yeah.
and you would have to overwrite it. You would have to look for it.
Find this-
Yeah.
Right,
So
get that.
Yeah, so from a asymptotic view, like once you bring this in, it costs you nothing to do the merge. Like so once you, from like in the ideal cache model, you're only counting cache line transfers. So once you have brought this node in to
That's
like,
just in there. More practical. So it's just in there. So it's in that.
you would
You're
have,
already searching in that node, sort of, or like put it in there.
if you're flushing this, you're already bringing this node in.
So I got that. I'm just saying when you put 79 to that node, you have to search if there's a duplicate for 79.
Yes,
That would go for every node you're pushing. Every key value you're supposed to push.
You already
Yes.
have to, like, the bottom nodes are sorted, so you already have to search, like, insert it, and you're already doing the search mechanism to put it in there also, so.
Yeah,
If
so
it's sorted, you can.
if it's sorted, you could do like a 2-finger scan.
You can, yeah, a binary search, or if it's not sorted, you have to go to that diagram.
Yes. Yeah. So that's another consideration, like whether you should keep these nodes sorted or not. And you could also like, you could keep the buffers unsorted and the bottom level sorted, like as a implementation choice. Thank you. Yeah. Yeah, so really good questions. That was insertion. For lookup, it's way easier. You're just gonna do pretty much the same pointer following search as you did in the B tree, but instead of just checking the pivots, you also have to check now each buffer along the way. So here, we're looking for 71. So we first look in the root and we don't find it. Then we follow the pivot and then we go one level down and it's still not there. And again, it's not there, but then we go to the leaf and it happens to be there. So we return yes. I guess I have time. Okay. So that is cool. And maybe I didn't prove this, but it turns out that that gets you like the asymptotically better insertion because now per the height of the tree, let me go back. Height of the tree is log base B. And you amortize 1 over b to the epsilon writes per level because you flush down a whole bunch of elements in your block. So that's how you get less than log base B insertion without paying asymptotically in your query. Does that make sense? So the way, okay, maybe I don't want to go all the way back in the slides. Okay, so the height of the tree is log base B of n, okay? And so you have to go down this many levels, but the cost of your insertion is like how many writes does it take you to go down this many levels? And I claim that the number of writes per level is 1 over, it's like order 1 over b to the epsilon.
Isn't the height of the tree one of log base B the epsilon?
Yes, but if epsilon is a constant, this is log base
Oh,
B.
okay, I thought epsilon was perfect.
Right, so yeah, good point. So the height, this is the height of the tree, and this is amortized how many writes it takes you to move down the tree at each level. And so when you multiply these two, then that is how you get the write complexity, which is log base b to the epsilon over b to the epsilon. Yeah. Mhm. Okay, so one more thing, I guess, that I want to talk about for now is some costs to be epsilon trees that don't show up in the asymptotics, but matter actually when you do the implementation. So recall, like when you do the insertion in the B tree, you have this buffering thing, and let's say this is your node, and now you get some new elements coming in, and you have to write your elements into your buffer. Well, first you have to look at your node, and then you have to put the elements into the node. So yeah, so we're gonna merge those new elements into your buffer. Like that. And here yellow means that they had to get rewritten. And I guess here we're maintaining them in sorted order. So those are things that had to get shifted and written when you did this merge. And again, like then you have to write this node back. And so like the work is proportional to the number of old and new messages that you got, because like in terms of just, not in terms of cache lines, but in terms of just straight up writes, you had to do proportional to the number of messages that you already had, plus the number of new messages that you got. And similarly, for the number of IOs that you have to do is also proportional to the number of all the new messages that you got. And this doesn't show up in the in the cache line transfer counting, but it does show up in other measures. So like again, let's say we had this example, we got some more stuff that came in. And now we have to, if we're keeping this in sorted order, we have to rewrite some stuff again. So that's why it's orange, because we had to write it twice. And again, like some more and more stuff comes, and you're rewriting some of the data several times until you get to do a flush. And your older data gets rewritten over and over again. And it can be written up to b to the epsilon times per node.
So does it help if we don't maintain the order?
Will it help if you don't maintain the order? It might help a little bit. You still have to rewrite when you do a flush because you like want to compact them. So it might help somewhat if you don't maintain the sorted order, but you would still have to be rewriting the data repeatedly.
Do most implementations usually maintain sorted order? Is that why we're talking about that?
I think it's easier to maintain them in sorted order because of this two-finger merge thing.
Aren't we getting the entire block?
Sorry?
Aren't we getting the entire block?
Yeah. So this is not showing up in the cache line transfers. This is just like a more practical issue with these trees. Which is like, I'll talk about it in a second, but like, it is not ideal that we keep rewriting the data.
Does B-tree also have this problem?
B-tree does not have this problem because, well, B-tree has this problem in the leaves because you're rewriting the leaves. Like you have to maintain the leaves in sorted order. And when you insert into the leaves, you may have to shift things around, but you're rarely writing to the internal levels. But in B epsilon tree, you're always writing, like you always have to write to the buffers. The number of times that you have to, like the particular number of times that you have to rewrite the data depends on the input. Like if the input came in sorted order, you would just be able to like append it to the end. Yeah, so yes, the number of times that you have to rewrite it does depend on the distribution of your data. It's okay, because the way that you choose the pivot is always like halfway in your node. Like, so like the tree will never become unbalanced because you're always picking the midpoint. The pivots are, when your node becomes full, the pivot is chosen as the middle element in your node, or the middle element among the pivot elements in the node. The thing to promote. Okay, so yeah, so this is the thing with buffer trees is that you have to keep rewriting the internal buffers rather than in a B tree where you're often always writing to the leaves.
The volume of the input output actually different in this and say when we insert in a B tree, because when we're inserting in a B tree, we would, or B plus tree, we would need to go all the way to the
That would be log base B of n reads per.
And then we can insert it back, right?
Mhm.
In this case, we're just fetching with one cache line or cache block and writing things there. So would the total volume of data actually be different?
It would be different because in a B tree, you have to fetch the data, but you're only usually have to write into the leaves, and only rarely do you have to promote into the internal levels. Like not every node, not every element will have to write into the internal levels in the B tree.
We see the accessing.
Yes.
So that would count into volume.
Yeah, so I think maybe you would be doing the same amount of read, but more write in the B epsilon tree. Yeah, thank you. Okay. Yeah, so there's two other metrics when you talk about the performance of cache-friendly trees or cache-friendly data structures in general. these are not reflected in the ideal cache model or stuff like that, but they're like practical concerns. So one is called read amplification, which is the ratio of the number of blocks that you read from the disk versus the number of blocks that you actually had to read. And the other one is write amplification, which is similar. That's like the number of blocks that you had to write versus, or sorry, the number of blocks that you actually wrote to disk or memory or whatever it was, versus the number of blocks that you were technically required to write. And if you have high write amplification, it turns out that it shortens the lifespan of your disk, like your SSD or stuff like that. And buffering increases the write amplification because you're always rewriting the internal nodes.
I'm usually saying like required is just how many that key value pair takes up, even for write. Like
Yeah, from, I guess, like, yeah, compared to like just the bytes of the key value pair.
Mhm.
Because in a logging sense, like you could just always
yeah, we're
append
not
at the end.
doing
Okay, so yeah, and there's a pretty recent paper in 2020 that talks about how to fix that. But I'm not going to go into the details because I am out of time for today. Thank you. We'll continue next time.